Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves? This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky, while Dr. Zook is pulling its other end towards himself and then pushing it towards Emily. Watch closely, and you will notice that some of the coils crowd close together and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid, liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Sound waves travel in all directions. Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo. Bouncing back of sound is purposefully used in detecting depth of seabeds. That's amazing, isn't it? Summary. Every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Bouncing back of sound is called echo.
Many of us take for granted a very extraordinary organ, our ears. To understand the ear, we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves helping us to determine direction of sound and emphasize frequencies needed for human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound passes along, the force is amplified by leverage until it arrives at the stapes, which acts like a piston, creating waves through the fluid of the inner ear. The most significant increase in force comes from a system of hydraulic amplification. The face of the stapes has a surface area of 3.2 square millimeters, while the eardrum has a surface of 55 square millimeters. Using this, along with the leverage through the malleus and incus, the final pressure is 22 times greater than when the sound first arrived. Now, we arrived at the most complicated part of the hearing, the cochlea. In reality, it is coiled up, but it is easy to understand straightened out. The stapes is causing pressure waves to travel through this structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, it encounters fibers with the correct resonant frequency and energy is released. These fibers are not actually what give the signal to us that we heard something. There is a special structure containing hair cells next to these fibers. When the fibers resonate, they cause the hair cells to move, which then sends an electrical impulse to the cochlear nerve and on to the brain. Certain pitches of sound will resonate in specific locations, and louder sounds will cause more hair cells to move. Our brain interprets all this raw data, making it possible to enjoy a beautiful song or a conversation with a loved one. Just to think that all this is happening in your head right now at full speed. And not just one, but two of these sophisticated instruments are helping you to have the amazing sense of hearing. This is just one of the many systems found in the human body that go far beyond our humble human understanding.
Two of the basic properties of sound are frequency and amplitude. Frequency can be thought of as the pitch of the sound, or how high or how low it is. Amplitude can be thought of as the volume of the sound, how loud or how soft it is. The first string on a guitar is very thin and makes a high sound. The sixth string on a guitar is very thick and makes a low sound. If you look at the picture that represents the sound, called a waveform, you'll find that the horizontal space between the waves is the pitch, or frequency. It's how frequently the wave is repeated. A low sound is spread out. A high frequency sound is closer together. The amplitude is the vertical height of the wave. The taller the wave, the louder it is. As the sound diminishes, it turns into a straight line.
You'll need a shoebox, some scissors, a pencil, and a few rubber bands. Mark the center of your shoebox. Punch a hole in it with your pencil. Around the hole, draw a large oval shape, like this. Use the hole you punched to start your scissors. Cut out from the center to your line. Try your best to cut out the whole shape. Great. Time to attach your first string. Take a rubber band and stretch it around the box. Rubber bands can snap, so be careful that they're away from your eyes. Stretch all your rubber bands around the box. Now you can adjust them into place. Separate them nice and evenly. Great. Use your pencil to create what's called a bridge. Now you can tune the rubber bands by making them tighter or looser around the box. Oh, that's lovely!